Bitch, I'm not creating a live event. Fucking YouTube being a fucking bitch again. YouTube's always being a bitch, though. Is it working now? Are you ready? Are you ready? Are you ready? Okay, cool. It's good. I don't know if I don't know if the function here. Gotta mute, gotta mute. Can I pin? Okay, I can. I'm gonna pin that. So we're going to talk about some core functions and features of the Monero FMPC, pretty much FCMP++. Some vulnerabilities that do exist within the Monero ecosystem. This is why it's important and kind of good to look at what breaking Monero is. They talk about some of the core issues of it, but I want to, before we just talk about just the issue, it's also understandable and good to talk about what is essentially what FCMP++ is supposed to solve. Now we kind of understand this is something that you understand that, like, if you understand what ring signatures are, this is kind of like a gloss over of what Monero can do, and they've talked about different ways to implement a more private way to kind of like hide and make Monero more private. Now, ring signatures in a simple fundamental way to stand. So pretty much Monero's address scheme is private from the sender to the receiver. It's built with security in mind. It's built with privacy in mind, kind of from like the ground up. It fakes 16 transactions on the blockchain, and it adds plausible deniability. These are the core fundamentals of like how the ring signature kind of works. It's based on math. The math does essentially what it does and it's supposed to do. There are some limitations of it, and there is some privacy vulnerabilities in it, but most of this is kind of done to like through human error. Essentially not running your own node is one of the biggest problems. It's something that you should always consider. Even if, say, hypothetically, if full chain membership proofs. Okay. Sorry, I was reading something. If you kind of understand like how it works, then you kind of get what the full chain membership proofs is. It is in testing that phase now. They are looking for people to test it. They're also looking for Carrot, I believe, which we can kind of like read overview. This is actually, if you want to test it, you can do the FCMP++ Carrot Alpha stress test. But we're going to read that in a minute, so just give me a second. Don't worry, guys. So we're gonna kind of like go over what the carrot is. What the carrot is. It's not that long. It's some math. And then also what it kind of solves. And then we're going to discuss, where is it? A section in Breaking Monero called the Poisoned Outputs and EAE Attack. It's about 30 minutes. I'm going to give maybe we'll watch it in like 2x speed or something. And E the goat. So Breaking Monero is essentially a really good series to still watch. We're just kind of gonna like break up the, obviously not in order. This is 6 years old, so keep it with a grain of salt. This still might be implemented, and it still might not be an issue in current 2025, but I think it is still an issue. I think EA attacks are still a problem. But we're first going to read what full member chain member proofs are, membership proofs are, and then we're going to go over to the other issue that exists, not issue, but like the solution, which is that. There we go. Okay. The fuck? Okay. So full chain membership proofs are as a concept is a replacement for rings within the Monero protocol. While rings have offered a sender privacy, Monero since it launched, they are vulnerable to attacks such as the EEA attack, have difficulties upon chain reorganizations, and in general enabled statistical analysis mitigated by distribution of the decoy selection algorithm. Full chain member proofs prove the output spend is one of any output on the chain, effectively removing all these risks. This means every input goes from an immediate anonymity set from 16 to 100,000. That is huge. That is a very important number to understand. So previously, before the set ring signature count at the time was 11, they implemented a way to people could theoretically pretty much make the ring size whatever they want. This, from a privacy standpoint, is not good, and ultimately it increased fees. It increased network bandwidth and fees because people would put like 1,000 or like 2,000 ring signatures. Well, that looks unique, and that uniqueness is not good because you kind of want everyone to look the same. That is generally you're getting what from herd privacy, like where all the sheeps look the same, all the wolves looks the same, everyone kind of looks the same. It's hard to distinguish between it when it's being looked at from a chain analysis standpoint. Full chain proof billion. So 2 proposals have been made for the Monero offering offering such privacy, both under the full chain memberships proofs moniker. Further mentions acronym to FCMPS with after Seraphis. Seraphis distinguishes between memberships. The output spent is one of some outputs and spend authorization. The output being spent is authorized by the private key holder. With that, much more efficient proofs for memberships became possible, including the Grudel proofs, which was originally proposed with effectively ring of 128. That would be very nice. In theory, 128 outputs is kind of crazy to be able to figure out. If you could figure that out, I mean, even 16 is hypothetically very difficult to kind of figure out our guess, because the realistic thing to understand is you have to remember a misconception with Monero is the fake chain, even though there are 16 output transactions with the ring signatures, Monero addresses schemes as private from the sender and the receiver standpoint. So we're gonna improve on the ring signature and privacy of Monero. Damn math people. So FCMPS, the full chain membership proofs, further improve upon this, requiring Seraphis new key transaction format to do so. The second proposal was made of March 2024 in response to the spam attacks. Is your encryption note app in C? No, it's in TypeScript, and it's all browser. It's all browser based. So it's a progressive web app that does the encryption scheme based on the browser. And it's all stored. Your keys are stored locally. It's got I can actually pull it up. I just installed an Arch on a Linux on a vape. Nice. Won't be here for long, see ya. Any on top, any is written in C. Nice. I don't know what any is. The fuck? I'm gonna fucking when I find it, but we're gonna go back to. See if I can get this. Mm-hmm. Damn it. I don't know if I can find this. Damn it. File. Hmm. It's called. Man, that's crazy. I don't know where the fuck that file went. Sometimes I hate files, man. I really hate the file system. Alright, whatever. Local send can be like the biggest piece of shit. I swear. It's such a great option, and then it ends up being the biggest piece of shit. And just functions is unbelievably awful. Like sometimes local send doesn't make sense. I'll send it and then I'll search for it. And then I don't know exactly where it went, but whatever. There you are. Damn, I got distracted. I got distracted. Hmm. Damn. Okay. Whatever, I'm just gonna forget that part. 27 wasted 27 minutes of your guys' times. Perfect. So that's how we do. Wow. Yeah. But that's it. We're gonna discuss FCMP. We're gonna go back. I'm the worst host on the planet. My ADHD be kicked in. All right. So pretty much in minus the clicking around and the retard shit that I was just doing. Essentially, it makes like pretty much 100,000 like different requests. The two proposals have been incorporated. FCMP ++S independently adds the spend authorization plus linkability, removing the dependency on Surface. With further research and development, it was found to add several new features to the Monero protocol without requiring the migration to Surface. These features include transaction chaining. The transaction chaining allows signing a transaction, spending another transaction before the spent transaction is published and mined on chain. This enables a certain layer 2 design for the Monero, such as payment channel protocols. Ongoing view keys allow anyone with the outgoing view key to detect whether they receive the outputs are spent. Currently, Monero only offers incoming view keys, which do allow detected spending with eventually high likelihood over the current protocol, yet don't provide 100% certainty. This certainty will make cold wallet setups and multi-signatures much more efficient, having to bring the private key online far less often. It allows defining a single view key without delineation of incoming or outgoing, simplifying wallet UX. Forward secrecy means that an adversary with a discrete log oracle, such as an adversary with quantum computer, cannot break the privacy of the protocol. While Surface also introduces these features, it does so with migration to a new anonymity set and a new address format, invalidating all prior addresses. The FCMP protocol not only aims to be faster to deploy, it yet to do so without the migration. This is enabled by the trade-off of not actually offering any of the functionality at launch. However, the deployed protocol would support all these features. The wallet code could take an average advantage of what it would of it would be delayed, ensuring that we keep our scope small and achieve the largest goal: full sender privacy as soon as possible. Wallets could then start taking advantage of these features on their own timeline without further hardening, forks, nor privacy issues. It would likely be done by merging the Surface codebase into Monero, taking advantage of its years of development and improved design. With that, migration to the new key structure would be optional, and if so, the work done on FCMP++S would provide the most of the necessary work for the FCMP's S with Surface. FCMP++S are based off curved trees, and to make the overall proof much more efficient, Egan's work with the elliptic curved divisors. The overall composition has been largely specified as currently being reviewed and further detailed as appropriate. The development of the composition was funded and embarked fund for academic review, and audit is still raising. If you're a member of the academic community and are interested in contributing, please feel free to reach out with the Monero Research Lab on IRC or Matrix based. So that's essentially what it is. It increases that type in perspective. So this is something that you should keep in mind. Okay. Carat is crypto note address on randomizable ring CT output transactions. Is an addressing protocol for the upcoming FCMP upgrade to Monero, which maintains the backwards compatibility with existing addresses. It does this while bringing new privacy and usability features such as outgoing view keys. Carat is designed to be indistinguishable on chain from another potential addressing protocol, Jantis, which will justify some seemingly strange design choices later on in this document. That is something to keep in mind when you go to a completely new protocol or a scheme. You kind of can get fucked if you have to migrate everything over to the new scheme. If you have to do it over the new scheme, then you potentially could fuck yourself in the long run. Because if it's a new scheme and that scheme isn't as efficient, then people might abandon the project or Monero altogether if it makes it difficult or if they lose access to their funds, etc., etc. Or it becomes harder to send funds or whatever, whatever it may be. And we're going to go through this. Just give me a second. Okay. Okay. All right. Let's leave. Let's read. Don't worry, guys. So the background: crypto note address, integration address, and subaddresses. In 2013, the crypto note white paper introduced an addressing scheme, which remains a crucial component of Monero's privacy model today. providing recipients unlinkable across transactions. Unlike Bitcoin, which uses a transparent address, Monero's use of addresses ensures that all created transaction outputs cannot be attributed to any single receiver, regardless of the number of times the addresses were used, and without recurring interactivity. So something that's important to know is you could theoretically use the same address, and you most likely, in most cases, will be safe. That is, with a grain of salt. There probably is some privacy concerns with using the same address in any form factor. Even the developers and the research labs tell you to use different addresses for different things to ensure that the linkability is not there. In the beginning, since there was only one address per wallet, this method was needed for receivers to differentiate from their senders. Payment IDs, an arbitrary 32-byte string attached to the transactions, with the initial solution for this problem. This aim was that send users sending funds would include a 32-byte message that gave the recipient user enough evidence to attribute the transaction to them. Integrated addresses improved the UX design of these payment IDs, having the recipient's wallet generate and include them inside the address, which were automatically added to the transaction data by the sender's wallet. They were also shortened to 8 bytes. Wallets then started encrypting the payment IDs on chain and adding dummies if no payment IDs were used, which greatly improved privacy. Kind of based. FCMP++. In order to tackle privacy shortcomings with Monero's ring signatures, there is a consensus protocol update plan called FCMP++, an abbreviation of full chain membership proofs plus spending authorization plus linkability. In contrast to ring signatures, relatively small decoy sets size, FCMP++ enables all transaction outputs on the blockchain to be used as decoys for each input. FCMP++ deterministic anonymity avoids almost all undesirable edge cases and target attacks against ring signatures, as well as improving on the normal in a normal case. To read more about MC++ upgrade, the original author wrote a blog post outlining new features, academic work, etc. Is that the one? Okay. Because you got to remember, guys, the most important thing to grasp at this is that all this mixing and optional privacy is kind of a problematic viewpoint in the Monero space, and most importantly, when you look at it at the greater you pull out and look at the greater view, when you have to mix, that means you have to have other participants, and you have to have you might end up with like dirty Bitcoin or whatever, and then same thing with Monero. I mean, not Monero, with Zcash, it is optional privacy. The shielded transactions, only 25% of transactions are shielded. They're estimating between 20 and 25%. That means there is historically a small amount of people that are taking advantage of these shielded transactions, and it is problematic, given the fact that Zcash has been around for quite some time now. Long, if not a little bit, about the same amount of time as Monero. So why would you add an extra step for people to do to maintain privacy? Now, obviously, Zcash sales and their board of directors, which are a bunch of that's just fucking retarded, in my opinion, can give up any reason they want to justify how stupid this is in general. That'd be like having opways or upside down, something like arbitrarily, even as a switch, turn it upside down, it becomes encrypted and no one else can use it. Average user is not going to think about that or go on with that. That's just like not really a good case. And then say 25% of the people, say you have thousands and thousands of users at this point, only 25% of them are using this. That's not a flex or a win. That means that people don't still see the value in it. See, when I buy Monero, I don't want to know, I don't need to know if it's secure or private. I know it just is. That is the point. it's kind of like Signal. Signal, you don't need to tell your friends or like anybody that you're using Signal with. It's like, oh, it's using this quantum safe encryption scheme, and they you know what I mean. You just got to say, hey, it works, it's functional, and it does have some privacy implications, and it is secure. That's really about it. The average user doesn't fucking care. So, and because they don't care, you need to kind of like enforce this type of scheme for them, so that it's harder for them to make mistakes in between in order to be functional. Now, if tomorrow Monero wakes up and it's like optional privacy, I would obviously abandon it, and find something that's better, that it guarantees that it's privacy by default. That's the issue. This isn't something like where people, it's not like a password to like a service where you should have an expectation that it is not private. This is a service that is emphasizing that we are private. This is this cryptocurrency is core functionality is we want to be private. We want privacy by default. So, I think it's the most logical approach, especially when it comes to it. The fact that it looked at Bitcoin is like, wow, that's probably not good that everything is public. Your money is public. It makes it less fungible. It makes it less secure in general. These are just things that you should think about. But I digress. Where Carrot fits in. Carrot is an addressing protocol designed to be layered on top of the consensus protocol, FCMP++. In other words, FCMP++ dictates the rules that transactions must follow in order to be valid, whereas Carrot provides a shared framework for how to transmit funds and otherwise interact with addresses meaningfully on the FCMP++ transactions. Carrot also contains a recommended wallet specification detailing how to construct public and private keys in a way that's best leveraged FCMP++. A wallet with a Carrot key hierarchy can expect flexibility on how wallet functions can be compartmentalized, as well as unconditional forward secrecy for change outputs, etc. However, an equally important design consideration is backwards compatibility. No one can participate in the current address protocol using pre-existing crypto node addresses, subaddresses, and integrated addresses. No wallet key migration is required. Even without a migration, using the Carrot addressing protocol provides protection against the burning bug attack, conditional forward secrecy, etc. The exact breakdown of which wallets will feature the outline in the following section. Furthermore, addresses generated by the new Carrot wall key hierarchy will be the same format as old addresses. Indeed, these new addresses will be completely indistinguishable from old addresses, maintaining off-chain privacy and easy development. I just realized dark mode should be enforced. We're gonna be doing C stuff on the stream today too. We're gonna learn C as we go. All wallets. Carrot immediately brings these features to both newly generated wallets and existing wallets. Address conditional forward secrecy. As a result of leveraging the FCMP consensus protocol, Carrot has the ability to hide all transaction details, sender and receiver amount from third parties with the ability to break the security of elliptic curves. Nice. Quantum computers. As long as the observer does not know the receiver's address. Wow, very based actually. Very cool. Very awesome. The Janus attack mitigation. A Janus attack is a target attack that aims to determine if two addresses A and B belong to the same wallet. Janus outputs are crafted in such a way that they appear to the recipient as being received to the wallet address B, while secretly using a key from an address A. If the recipient confirms the recipient of the payment, the sender learns that they own both address A and B. That's not good. Stateless burning bug mitigation. The burning bug is an undesirable result of Moneros' old scam process where if the exploiter creates a transaction with the same ephemeral public key, pub key, and transaction output index as an existing transaction, the recipient will scan both instances of these endnotes as owned and interpret their balance as increasing. However, since key images are linked to output keys, the receiver can only spend one of these endnotes, burning the other. If the exploiter creates an endnote with the amount of A equals 0, and the receiver happens to spend the endnote that first, then the receiver burns all the funds in the original endnote with only a tiny fee cost to the exploiter. Interesting. An initial patch was introduced secretly to catch when such attempt attack occurred. However, this patch did not attempt to recover gracefully and instead simply stopped the wallet process with an error message. Further iterations of handling this bug automatically discarded all instances of publicated output keys, which didn't have the greatest amount. However, all instances of burning bug handling in Monero could require a complete view of scanning all history up to the current chain tip, which makes the workaround somewhat fragile. The original Jamtis proposed by Tevador and the guaranteed address proposal by K-Band Nerve were some of the first examples of addressing schemes where attempting to burn in this manner is inherently computationally intractable. These schemes somehow bind the output public key to an input context value, which is unique for every transaction. Thus, the receiver will only ever correctly determine the endnote given with the output public key to be spendable for a single transaction, avoiding the burning bug without ever having to maintain a complete scan. Carrot prevents this attack statelessly in the same manner. Payment ID and confirmation. Payment IDs are confirmed by a cryptographic hash, which gives integrated address payment process better guarantees, provides better UX, and allows many output batches transactions to ambiguously introduce the integrated address destination. New wallets only. These features are only available to wallets generated with the newly defined account key hierarchy. Existing Monero wallets will not inherit these features, unfortunately. So we're going to look at what this will only be affected by new wallets. These features are only available in wallets generating the newly defined account hierarchy. Existing nodes are unfortunate. Internal forward secrecy. And notes that are sent internally to one's own wallet will have all transactions details hidden, sender, receiver, and amount from third parties, with the ability to break the secrecy of the elliptic curves quantum computers, even if the observer has knowledge of the recipient's address. Address generator tier. The tier is intended for merchant point of sale terminals. It can generate addresses on demand, but otherwise have no access to the wallet, i.e., it cannot recognize any payments on the blockchain. That is super important to understand. Any linkability reduces the ability of plausible deniability. Payment validator tier. Carrot supports view incoming only wallets that can verify that an external payment was received into the wallet without the ability to see where those payment emotes were spent and notes were spent, or spend it themselves. But unlike old Monero view-only wallets, the Carrot payment validator wallet cannot see the internal change in notes. Full view-only tier. Carrot supports view-only wallets that can identify spent outputs, unlike legacy view-only wallets. So they can display the correct wallet balance and listing all incoming and outgoing transactions without the ability to spend anything. Whew. Okay. Miscellaneous definitions, the function, okay. Hash functions, the function, elliptic curves. We define a function, okay. Creating a transaction output, spending a transaction output, some other maths. Address generation, there are two cryptographically distinct addresses, types in Monero, CryptoNote, and subaddresses. Note that the integration addresses are derived exactly like CryptoNote address, but they have an additional payment ID. This can only be a maximum of CryptoNote addresses per view key. Interesting. Handling the key images, security properties, balance, recovery, security. Completeness, note, scale, blinding, forward secrecy, indistinguishability. Okay, interesting. That's interesting.
Episode on poisoned outputs for the EAE attack or NAC attack. It's given several names, and we are here to discuss this pretty honestly difficult and nuanced topic to talk about, so we'll do our very best. We're here with me, Justin. We're here with Suray and Sarang. It's great to have everyone here on. So this video is going to be diagram heavy. So if you're watching this on like a podcast, we'd recommend watching video form later if you're confused, because there's really a lot of stuff going on. But first, we're going to have Suray talk about like what's the general idea of sort of marked funds that we're sort of talking about, and then I can jump into the diagrams to explain the situation to you.
All right, so here is a thought experiment for everybody in the Breaking Monero audience. Let's say that you are living in an oppressive society and you want to buy some banned books. And let's say that you have a local banned book.
6 years ago, this is crazy.
Dealer stands on the corner and you can go give them cash and they will give you your
Because, like, there are people that are banning books quite recently. Like, anyone who bans books is fucking insane.
Bible or your To Kill a Mockingbird or whatever copy of banned textbook that you want. Now, one question you might have is how would this tyrannical government come to the conclusion that you are a purchaser of these devices? Or rather, how would they go about tracking the person who is supplying all of these banned books, these nasty little devices, to society? Well, one way to do it, and this is how law enforcement has done this, this is like good old-fashioned police work going back hundreds of years. You'd go do a controlled purchase from one of the street dealers. You'd go buy a book 6 or 7 times in a row, and then you look for bank deposits at local banks. And what will end up happening is this street dealer will go give the cash to his boss or one of his boss's minions, who will then hand it over to the boss, and then eventually it'll make its way into a deposit at a bank account. And if those dollar bills that were used to purchase the banned books were marked, the bank will alert law enforcement, and they will have found their kingpin boss who is depositing money from these controlled purchases. So the essential idea is person A is purchasing something. Person E is purchasing something from oh man, I screwed it up. So the main thing is that somebody is buying a book, and there's going to be a chain of custody of the money that will eventually end up in some Know Your Customer bank's hands. And once that money ends up in the bank's hands, they can start linking real life identities with those original purchases and find that.
True. They've even said that, like, cash could be theoretically kind of like looked like tracked. It just depends on like but cash kind of like depends on the location, and it kind of depends on like where you bought it and like what's like left in terms of what's left in terms of linkability.
The interior hops of those transactions. And unfortunately, this is a problem that Monero faces. I'll hand this back to Justin.
Excellent. So we're going to take a look at this attack in a little bit more detail, just to show people what it is. Now, again, a warning: this is very this is a very heavy series of slides, so sort of brace for impact here. And I'm going to try to get my cursor up here, laser pointed. Perfect. So, as discussed, you have person Eve that is sending funds to a specific address. The address with Monero 43 whatever goes on forever. And they're learning information when this person then takes funds and puts it on an exchange or some other colluding entity. It doesn't matter what these entities are. All that matters is that Eve is colluding with the exchange, or this party A is colluding with party B. Again, it doesn't matter who these parties specifically are. So let's say Eve sent a transaction to that address. They create a ring signature, as is shown here. They use their real output here that's related to Eve. And then they create a transaction with two outputs. One output is given to that address. We'll call it output A. And the other address, let's say, is given back to Eve. So Eve doesn't worry about this. She's not trying to track this output. Ultimately, let's say that Eve comes back, looks at the blockchain, and notices that there are 3 transactions that have this output in their ring signature. These are not associated by time or anything. Let's just say there are 3 transactions. And let's say, like this first one, again, it uses A, the second one uses A. They all use this one output. These are all the transactions on the Monero blockchain that use this output. And we're not sure necessarily that A is truly spent in these ring signatures. It could be a decoy in all 3, but they're still trying to learn information about what the situation is. So let's say for the second transaction here, for instance, that someone deposited this output on an exchange. This one yellow output here was sent to an exchange, and Alice was the person who sent the funds to the exchange. So for this E example, you have Eve as the first E, you have Alice in the middle, and then you have the exchange on the last portion here. So what we have to note here is like the exchange might suspect, in conjunction with Eve, that Alice is the holder of this Monero address. Now, this is a heuristic. It's not very strong, especially if there's only one instance here. We don't really know what the real case here is, right? It could be that.
And heuristics is kind of like important where they talk about this in there is like if, like, some people incorrectly describe, again, Monero when you are spending it with these 16 outputs that are, well, like I could just kind of guess what this output is. I don't really need to. I'm like a math person or whatever. Well, it's kind of like that's where the plausible deniability comes from. It allows you to say like you pick like a number between 1 and 10. This is how it was explained to me, and I kind of get it now. Number 1 and 10. Most people are going to pick either 7, I think, is a common one, or 3. They don't like 1 or 10. They don't like extremes. This is just like common. Like this is like a common, very easy to grasp mathematical statistic that isn't overblown or like just like there's missing pieces. Most people, irrational people, will pick like 7 or think 3 is like the other one, and essentially what you in this scenario, someone's going to be like, well, write down your number, write down your secret number, close it up, and I'm going to guess. They might guess all 16 times, and eventually they might like be like, oh, okay, we got it. But what the heuristics kind of like solves is the plausible deniability, because the lack of address linking, because it creates a one-time send address, is you wrote the number on there and they're like, is your number like 6? You just eat the paper, essentially. Like you eat the piece of paper instead of answering. Does that mean that you did anything? Not really. Not in like the most of the court of eyes. I mean, it might be kind of like, okay, why'd you do that? But you don't have to answer, because like you could be like, is this enough sufficient evidence in your country to not only catch for a crime, or provide linkability, or pretty much provide linkability. If it isn't, then you're good.
Alice just used this output in the sort of ring, used this output as a decoy in the ring, and if this only happens once, there's a pretty high chance that a high probability that this just happened by chance, that Alice is not the true person who holds this address. But if this happens twice, or the chance that one person that deposits funds on our exchange is able to have a possible really recent spend from the outputs we assign to this address is very low. It's a very, very low probability that this happens by chance. And so as a result, we're going to assume that there's a good enough amount of evidence that Alice is the same person as this address. And it's not the only sort of circumstance that can happen. This graph gets very messy, especially as you add other sort of situations. We're trying to really keep it simple for this episode, while nevertheless keeping, at least discussing some things that can sort of get in the way. So let's say for this ring here, that there is another output that was sent to the exchange, as I'm highlighting here. Well, in this case, maybe this was sent to Charlie, who sent the funds to the exchange. Well, the exchange probably would at least have some suspicion of Charlie, but it's far more likely that in Charlie's case it happened by chance than in Alice's case it happened by chance. But it's certainly some limitation of this sort of model. And it's a very sort of complex system on how these things get added. Ultimately, it is a statistical test to say, okay, what is the likelihood that this would have happened by chance, or what is the likelihood that this is actually what's going on? And you're going to have type 1 and type 2 error as you conduct these statistical tests, but ultimately, there are certainly ways for them to be much stronger in some circumstances than other circumstances.
You mind if I jump in really quick, Justin?
Yeah, sure, go ahead.
Maybe I should do 2x speed.
One thing I want to point out is just to connect this graph to this discussion I mentioned a little bit ago about controlled purchases. One way that you can visualize this is Eve is, for example, a detective who's purchasing banned books online. They've constructed these 4 purchases from this anonymous online vendor, 43WI. And then a couple of months later, maybe a week later, this exchange notices that Alice makes all 4 of these deposits. The exchange comes to the conclusion that these 4 deposits are probably related to the banned book settlement purchases. The difference is that in Monero, we have these ring signatures that point back to several previous vendors. So in the cash scenario, I have a chain of money going from one person to another person. Here, we have each output that is possibly multiple ring signatures and is only probabilistically implicated. So what you end up having is this exchange is capable of developing this probability profile of Alice.
Exactly. So we can even expand this. We're going to take this example and sort of do a little bit more with it. So let's say instead of Alice sending 4 different transactions to exchange, she takes even less precaution and decides that she just wants to send one big transaction here. So this one transaction has 4 rings. There are 4 inputs, each with their own rings. And so you see one of these is A, B, C, and D, and then this transaction is deposited on the exchange, again under Alice's account. Well, now we can be even more clear generally, because you have one transaction, like what is the likelihood that a single transaction would contain all of these 4 outputs that are being watched in each independent ring? Is very, very low, and especially as the number.
Yeah, so like not only if it's very, not even if it's just very low, and like the probability is low. Is because of Monero's address scheme is like very thought forward. Oh, that explains it.
Alice, if she was interacting with an exchange, should be concerned about revealing that she is, again, related to this one entity, this address, because it's highly unlikely that anyone else could be. In this case, it's very likely that this did not happen by chance. The errors are very low. Now, both of these were sort of with one layer of separation, where you, again, have like one person who sent funds to one intermediary who then sends it on to an exchange. But this could get even more complex. And so I'm going to show an example now where you have more intermediary steps. In this case, I'm only showing 2 because that's about what will fit on the slide, and even so it's simplified, but this could be much longer depending on what you're really assessing. So again, let's start out with a simple single transaction case. We have Eve here who sends one transaction to this entity, and this output is used, let's say, in 3 transactions. Of course, in all likelihood, it would probably be much more, but for the sake of being on the slide, let's say 3. Well, let's say none of these transactions were deposited on an exchange or deposited on a service that Eve is working with to learn more information. So what Eve might do is say, okay, well, even though I didn't learn anything specifically from these set of transactions, I'm still going to watch these new outputs that are generated. So instead of watching these 3, I'm still going to watch doesn't come with any initial red flags, and the first transaction to immediately use B. But let's say that in the second set of transactions, that there was another deposit to be exchanged, and Alice. Thus also make this deposit. Well, now the exchange you start to get a little bit more information about who actually deposited these funds, because now you're starting to have enough strength in a statistical model to say, well, now it's unlikely that Alice would have deposited both sources of these funds if they did not receive outputs A and B. So it's really important to show how this grows over time. It gets more complicated as you have more layers to this. And to sort of simplify it, I have a nice stupid example here, where we have a transaction tree, and it purposely looks very much like a pyramid here. But let's say that like one user, so for each tree here, this is the depth of an output as it goes on. So you have your initial transaction here that generates outputs, that generate more outputs, so on and so forth. And this tree gets bigger and bigger over time. So if you have two people that are involved on both sides of the transaction, again, let's say that Eve here sends funds to Alice, who then sends funds to an exchange really early on. Well, there's not a very deep transaction graph, and so Eve and the exchange have at least a decent idea. They can do a statistical test that has a pretty high degree of probability. But if there's only one test that's all the way down here, there's a ton of other entropy that could occur, the statistical test is far weaker. But if a user does this twice, so that sure it might be deep down in the transaction trees, but there's several trees that they can collect information from, well then the test starts to become stronger again. So ultimately, in summary, and this can be applied to really any sort of application of these statistical tests, the more points of information that the user has, so the more trees that Eve, the exchange, or any sort of observer is able to construct, and the further up the tree that the outputs are, or ornaments, maybe in this picture example, right, the better the statistical test. So as users have, as you have more instances of information about a user, and as there's less ambiguity for those sets of information, the statistical tests get stronger.
Okay. Okay. Interesting. Okay. This guy says, really great diagrams, very nice. I added a few things in the case they aren't obvious. There don't need to be controlled purchases in order for the attack to work. All you need are entities to know their identity. Keeping a record of the quote-unquote serial number of each output they give or of you receive, which is wallets and exchanges and various probably all do by default. This means that a single exchange can see a lot of transactional relationships between users, e.g., if on the multiple occasion the exchange sends money to Alice, Alice sends money to Bob, and Bob cashes out the same exchange, then these exchanges can see the relationship, thus, closing the gap on some form of anonymity. It also means that if the money isn't returned in a loop to that exchange, but if a vendor is subpoenaed or has a data breach, the exchange can use the link vendor wallet to determine which exchange customers regularly do business with the vendor. Many exchanges and vendors can also collude to be collectively subpoenaed or collectively be the source of a data breach. This would allow the relationships between to be determined between user transactions on a multiple occasions. Between those multiple parties, nothing has to be poisoned in advance. The data is all being collected and stored. It is simply waiting for someone to mine it. It should be that the data ever leak, otherwise become available. Here's an original write-up. There is an analogy for how Monero works, which that is, it's like a crowded dance floor where people randomly dance wearing a face mask of strangers. We need to get people to dance more so that it is really a crowded dance floor and not an empty hall where people occasionally only appear. I do think that if we can make the churning of received outputs individually prior to ever being combined with any other received outputs an automatic practice of this basic hygiene, it would be help enormously get off the dance floor. I kind of agree. The churning part is, I would have to ask them what do they mean by churning? Churning is, I always associate with requiring other users. Raising, what is this? Raising the mandatory ring size in the V6 Hanfart September 2017. This is from 2017. Interesting.
Stronger. And so now you sort of at least should understand the very basics about what an EAE or a poison output set of attacks are. It's the case where users try to construct as many, they try to be associated with as many of these trees as possible and to try and learn as much observable information from it as possible so that they can really get actionable information. And with that, I am done ranting.
I just want to say one quick thing, actually. I guess that we're not going to be able to go back to the diagram while I'm talking. So, one interesting thing is that, as Justin says, if you go to the bottom of the tree, right, the intuition is that you're going to be more likely to be hidden by obscurity, right? Security by obscurity as you get down lower to the tree, because you have more hops. As you go down into the tree, you have more and more options. But one of the interesting things about these trees is that if you go really, really deep, they get scraggly and unhealthy, and they don't have a nice full base like a good tree does, and so they get less dense as you go further down. So even though it seems like the further deep you go, the safer you are, if you go too deep, you may also be creating problems for yourself. And that's just one of these interesting properties of these tree structures. And I just wanted to throw that out there.
All right, thanks, sir. So, Sarang, can you talk a little bit about something about like how these attacks sort of get harder? What some of the implications are in a little more detail about like how the statistical probabilities for these tests sort of is determined.
Right. Well, I mean, so they're determined by a few different things, right? So you kind of talked about two different aspects. You talked about the number of trees, which of course, in part, that just kind of depends on how the adversary is doing control purchases that may be out of your control depending on your circumstances. The one parameter that we do in fact control, we talked about pretty frequently, is ring size. Ring size, of course, is the number of different outputs you're kind of throwing around each ring, which affects in some ways the level of plausible deniability you have that you're the spender of a particular transaction. So in that particular circumstance, the idea of kind of working your way down this tree and changing the ring size can in some ways almost kind of affect the width of these different trees. So in particular, every single time that you kind of go one layer deep on the tree, a bigger ring size will, in general, kind of depending on transaction volume and things like that, affect kind of how wide the tree is, and therefore how many different paths there are that can lead an adversary toward the statistical model of what's going on. So all of the things being equal, an increase in the ring size can, in fact, make this a bit harder for the adversary depending on how it's done. And of course, the number of times that you send funds to another entity. Of course, the idea of what's called churn is just sending the funds to yourself. Basically brings you kind of deeper and deeper down into this tree, which of course may lead you to believe, well, okay, in that case, why don't I just send funds to myself a bunch of different times before I eventually go to the exchange? That I'm far enough down the tree and said that that's good. But of course, the way that you actually go about doing those transactions, the timing that you use, for example, that could also, in fact, leak information if it's not done safely. So, timing data, that may be available to others looking in the chain, or to your ISP, who knows when you're online and things like that. Different types of metadata like that can affect the way that churn is done. Which is why when people say, how often should I churn? How should I do it? It's kind of a tricky question because it depends a lot on your direct model and not build up to any. So those are kind of two interesting parameters that kind of affect the way that these little trees are structured.
So, what about the point where, like, suppose, so how do you sort of avoid this type of problem though? Because, like, do larger ring sizes alone sort of help with this, where users don't need to care, or even with large ring sizes, do users need to care?
Well, I guess you can kind of take this to an extreme, right? The idea that, suppose that the ring size kind of got, as big as it possibly is. That is, suppose that every possible output was a possible decoy, and that every possible output would be used as a possible.
Something to think about.
Decoy. Then you kind of run into this large anonymity set situation that other, like Zero Coin or Zcash type protocols and assets have. Which in that circumstance, you're pretty much as good as you can get. Everything is equally probable as a spender. And trying to build this tree would be, absolutely incomprehensible. So to some extent, it does become really good. But it's ring size in our particular case is a parameter that does affect things like transaction time and transaction size. So it definitely needs to be balanced against what the possible benefit could be. It's definitely not a one-size-fits-all answer for what the ideal ring size should be. It's tough. It's tough and tricky.
And then we also want to make clear that the examples that I show were not exhaustive, right? There's a ton of different other nuances or different things we could have thrown in there that would either make the make the statistical tests far more or less accurate in practice. Imagine if they start bringing IP address metadata in, where they're going to be like, well, these transactions were also sent from this IP, or it's going to get far more involved. Or what if there's many people making deposits on the exchange, and so therefore there's a ton of different users that have similar behavior? Well, then it's going to become weaker, and so it's certainly it's not just a really sort of simple answer we're going to have here for you.
Well, interesting. My stream restarted. Well, guys, I don't remember how long I've been streaming because I ignored this, but thank you for stopping by. We're going to discuss this more tomorrow, and then we are going to dive back into C. Make sure to like and argue in the comments for the algorithm so YouTube knows that I'm